welcome you to my lecture today. Let me just say today we got a lot of mathematical work to work on, and majority of the work will be on the board. So I actually, uh, you know, encourage you guys to focus more on the board. Whether you are in person or online, you need to ask questions. If you want to ask questions, I will require that you talk. Okay, because if you chat with me, those of you that are online, I may not be able to see your chat. So the only way I can hear you is when you talk. Okay, so I'm going to show some slide uh, for the next 10 minutes, and after that, the rest of the minute is going to be on the board, and I need you to pay attention. Okay, so today we want to start focusing on expectation and variance of discrete probability distributions. Of course, you've been introduced to, you know, different kinds of probability distribution. Okay, and what we want to do today is just to have a kind of derivation of the mean and the variance of each of the distribution that have been introduced in the past. And that was why I called it in the learning goal. Okay, we want to focus on the properties of a discrete probability distributions. When we talk about properties, we're talking about what does it mean? What is the variance? What is the standard deviation? What is the skewness? What is the kurtosis? And so on like that. Okay, there was one distribution that I've not discussed, and I will need to start from that distribution, which we call the discrete uniform. When we talk about discrete uniform distribution, this is situation whereby we believe, you know, the possible event that we have in the sample space has equal chance, equal probability. And therefore, if the number of events in the sample space is n, in this case, I'm talking about the lowercase n, of course, the probability of occurrence of whatever event is going to be 1 over n. This is the probability mass function of a discrete uniform distribution. We talk about uniform. Of course, uniform means the same. They got the same chance. And what is the expectation? Today I'm going to show you how they would derive the expected value of x to be n plus 1 over 2. And now the variance of x is derived to be n squared minus 1 over 12. But before I go into derivation, I'm going to walk you through an example of a discrete uniform. I don't know whether, of course, some of you have seen a die, right? A fair die, right? A fair die has, what are the possibility? 1, 2, 3, 4, 5, 6, right? Now, the random variable is going to go from 1 to 6. And if it is a fair die, if the die is balanced, we expect the probability of any value within, whether the probability of x equal to 1, probability of x equal to 2, until you get a probability of x equal to 6, they're all going to be 1 over 6. They're going to be the same. That's uniform. Okay? So that is what you can see. So, and if you plot that, if you see what you can look at the graph now, you're actually going to see the height of each bar is the same when you plot. Okay, so the graphical representation of that is what you are seeing right now. This is what we call discrete uniform. Okay, now, if you want to, based on what you've done before, okay, how do you find the mean? How do you find the variance when you're a situation where you have a probability distribution given this way? Okay, of course, I taught you that before. You're just going to multiply the probability by its corresponding outcome. Okay, in the end, what do you have? 3.5. Okay, the 3.5 that you are seeing now is the expected value of x, which is the mean. If you want to get the variance, you need to first get the expectation of x squared. And after getting the expectation of x squared, then the variance can be found using the expected value of x squared minus expected value of s all squared, and the variance here is going to be 2.92. And of course, the moment I know the standard deviation, okay, the moment I know the variance, I can figure out what the standard deviation is going to be. The standard deviation is going to be the square root of the variance. But let me tell you this. Do you know, instead of going through finding this, getting the expectation of s, getting the variance, we can actually use the formula that we're seeing now. Okay, now what is n? Okay, how many? What is the cardinality? You know, n is going to be the cardinality of the sample space. Don't forget, the sample space in this case is this, right? So what is the cardinality of the sample space? Is basically 6. So if I want to use the formula of a discrete uniform, that is n plus 1 over 2, that would be 6 plus 1 divided by 2. 7 over 2 is what? 3.5. Now, I'm going to take you back now. You're going to see something now. Okay? What does that give? 3.5. Okay? This is making use of the expectation of x from the discrete uniform. Okay? Now, the formula here and that one is giving you the same results. Now, what about the variance? If you go back to the variance of discrete uniform, the variance of the distribution is actually n squared minus 1 divided by 12. So which is going to be, in this case, the cardinality of that? 6 squared minus 1 divided by 12. That would be 35 divided by 12. If you try to press your calculator, you're basically going to get 2.92. That's you go here as the variance. Okay, you can try and press your calculator. 35 divided by 12 will automatically give you that. You can now see the reason why, if we know the mean and the variance of a distribution, that will save us, time. Instead of going through all this, it's going to take time. Okay, now before I start using the board, I'm going to show you this again, because let me just tell you what we're going to do today. I'll show you when I have a discrete uniform. Okay, how do we derive the expected value of x to be n plus 1 over 2? How do we derive the variance of x to be n squared minus 1 over 12? Not only that, I'm also going to show you how we, of course, I've already showed you that of Bernoulli. Okay, I derived Bernoulli the other time. And from Bernoulli, I'm actually going to derive the mean and variance of binomial. Don't forget, the binomial distribution is a generalization of Bernoulli. Not only that, I'm also going to show you how to derive the expected value of s and the variance of s when you are given a geometric distribution. Not only that, I'm also going to walk you through how do we derive the one for the negative binomial. And of course, I've shown you in this class yesterday how to derive the mean and variance of hypergeometrical distribution. Okay, so that is all what I'm actually going to walk you through. And you know what I need you to do? Uh, in case you cannot see the board, those of you in class, I will advise maybe you shift forward if you cannot see the board, because what I'm going to be doing now, okay, from now up to the end of this class, I'm going to be using the board. Okay, so, and of course, tomorrow, I'm going to walk you through the moment generating function. Okay, I'm going to stop my share now and basically the board. Let me first ask this question. Those of you online, can you confirm if you can see my board? Can you see my whiteboard? Can you see the
Yeah, we
whiteboard?
have whiteboard.
Okay. Okay. Thank you so much.
The only thing I
Thank
would
you.
say is that that top S equals 1, 2, 3, 4, 5, 6. That is the
Yeah.
very top of what we can see.
Oh, you mean you can say that again?
The S equals 1, 2, 3, 4, 5, 6.
Yeah.
We we can see we can see that barely, but we can't see anything above that.
Oh, above that. Yeah. I'm gonna make sure I didn't write something above that.
Yep.
Okay.
Just to let you know, we
Okay.
can
But
barely
but
see
in
that.
case you can't see something, please let me know. Okay. I'm gonna make sure I write so big. Okay, let's get started. Like I said, you know, we're gonna make use of the board today. We're gonna show you some theoretical derivation, and if you can, for those of you in class, if you can't see the board, I will advise maybe you shift or move forward. Okay, we want to get started. I'm going to start with what I call discrete uniform. Okay, discrete uniform. Okay, now when you take a look at a discrete uniform, let me stop my share here. Okay, now for discrete uniform, okay, X follow what I call uniform distribution. Okay, now if X follow uniform distribution we have interval A B. Okay, the probability of X is 1 over n. Like I said, equal probability. It's just like you have something like this. You plotted this guy here against X. Okay, and this is A, this is B. Okay, by the time they got the same height, which is 1 over n. That's what I mean by uniform. Okay, they all have the same distribution. They all have the same probability. Now, when you take a look at what I have now, if I want to, how do I actually, if I want to find the mean of this distribution, because uniform is a discrete uh, probability distribution, okay, I'm actually going to do this x p of x for all discrete distribution. Okay, this is the formula for the mean for all discrete distribution. Now, um, if that is what I have, okay, so I have x sum, and here, x, this guy here is 1 over n. Okay, as you can see, it's 1 over n. Okay, and we're talking about natural numbers. S is going to start from 1 to n. Okay, in the case of a die that I showed you the other time, 1, 2, 3, 4, 5, 6. Okay, in the case of a die that ends in 6, right? Okay, we are talking about natural number. Of course, it's going to go up to n, 1 to n. Okay, so here this is a constant. Okay, I'm going to have x start from 1 to n. Let me just say xi, so now when you take a look at, or never mind, that's fine since I'm using s. Okay, so x start from 1 to n. If I want to rewrite that, it's like I got this 1 plus 2 plus 3 until you get to n. What do you have here? That is sum. This is like sum to n time of natural numbers. You need to go back to high school now. Want to go back to high school? If you go back to high school, okay, when you have something like this, sum to n time, okay, it's going to be n over 2 into a plus last time. If you remember sum to n time in arithmetic progression, what is your a? Your a is going to be 1 first time. N is the last time. N. So here I'm actually going to have n over 2, 1 plus n. Okay, take a look at that. So I'm going to plug in this guy here. So I'm actually going to have 1 over n. Okay, then this guy now, n over 2, 1 plus n. Okay, this guy cancel that guy. Okay, so what do I have now? Okay, I got n plus 1 divided by 2. This is the expected value of x. That is how we derive that. Okay, that is how we derive the expectation of x to be equal to that, n plus 1 divided by 2. Now, if I want to derive the one for variance, if I want to get that of the variance, so what I'm going to do, getting the variance of x is expected value of x squared minus expected value of x all squared. So right now, okay, we need to figure out this guy. We already know this guy is n plus 1 over 2 all squared. Okay, now I want to figure this guy out. Okay, so the expectation of s squared is summation s squared p of x. Okay, x start from 1 to n. Okay, so here now, you're going to rewrite this s start from 1 to n. Okay, s squared 1 over n. Okay, so 1 over n, okay, summation x squared, okay, s start from 1 to n. You know, if you remember this, if I have this and I have 1 squared plus 2 squared plus 3 squared until I get to n squared, you need to recall what you've done before. There's a formula for this in mathematical induction. You know, you did a prerequisite before coming here, right? Okay, recall that. What is it? What is the sum of square of natural numbers? The sum of square of natural number is going to be n into n plus 1, 2n plus 1 divided by 6. If you can recall this guy is for that. So this is going to be 1 over n. You see that? The n is going to cancel that n. Okay, so if that cancel that now, okay, so what I'm going to have, okay, so what I'm going to have is basically, so the expectation now, the expected value of s squared, I actually got n plus 1, 2n plus 1 divided by 6. That's what I got. So what is the variance? Okay, the variance is going to be n plus 1, okay, 2n plus 1 divided by 6 minus n plus 1 over 2 all squared. When I have this guy now, okay, I'm actually going to rewrite this as this divided by 6 minus n plus 1 squared divided by 4. So what is going to be the SCM now? The SCM is going to be 12. Okay, so if the SCM is going to be 12, I can factorize n plus 1 out. Okay, this is going to be 2n plus 1. So it's good. I'm going to have 2 into 2n plus 1 minus. Okay, so here I'm going to have 3 into n plus 1. Okay, so when you take a look at this now, so I got n plus 1. Okay, when you expand that, okay, when you expand that, that's going to be 4n plus 4 minus 3n minus 3 divided by 12. Take a look at that. Okay, so when you have that guy now, okay, so when you have that guy now, okay, the variance of x is going to be n plus 1. Okay, the 1 here, 4n minus 3n is going to be n. 4 minus 3 is going to be that divided by 12. So what is another way to write this is n squared minus 1 over 12. So therefore, the variance of x is n squared minus 1 over 12. Take a look at that. That's how that is right. Okay, so what have we just done now? We just derive the mean and the variance of a discrete uniform distribution. Any question before I move to another distribution? Any question before? Because the way I'm doing it now, when you check some textbook, you are never going to see it this way. Okay, like what I'm doing now, I'm like doing tutorial. Yeah, go ahead. Is it here or here? Here. Oh, here. Yeah. How many six do you have? Do you have in 12? Two, right? That is a two here. Yeah. And multiplying this guy. Does that make sense? Like this, how many four? The way having 12, that would be three. It's like you're doing uh uh yeah, fractional, subtraction of fraction. Okay, now this is how this for the discrete uniform. Now I want to go into another distribution now. I want to go into another distribution. Okay, now, and another thing you need to take note. What of if I ask you to investigate whether a distribution, okay, is valid. For instance, you have a discrete uniform. How do you show that, okay, it is a valid PMF? PMF is probability mass function. So if I want to show, I need to show that the sum of that over the state space of discrete uniform is going to be from 1 to n must be equal to 1. Okay, how am I going to show this? I'm going to do x start from 1 to n. Don't forget, 1 over n is a discrete uniform. How am I going to show that this is equal to 1? Let's take a look at this. 1 over n summation x start from 1 to n. What is the sum here? It's summing 1, right? When you sum 1, when you have like 1 over n into 1 plus 1 plus 1 until you get to n, what is it meaning? When you sum 1 in n time, that's going to be n, right? So if this is n, so I'm actually going to have n. What do I have? 1. Okay? So if you are given any discrete function and they ask you to investigate for its validity, okay, then when you sum it, it must be equal to 1. Every probability distribution of the discrete type. By the time we're going to start the continuous one, we're going to be talking about antiderivative. But right now, we're not talking about that. Okay, now I want to move now to binomial distribution. But before moving to binomial distribution, in this class, I've already proved, okay, for the case of Bernoulli, okay, because there's a connection between binomial and Bernoulli. So if X follow Bernoulli, or parameter that, of course, the probability of this is basically going to be p raised to power x 1 minus p raised to power 1 minus x start from 0 to 1. Okay, now if I've already shown you in this class that this guy is going to be that, and the variance of s is going to be p into 1 minus p. I've already shown you this for Bernoulli. So if you want to derive the one for binomial, because the binomial is a generalization of Bernoulli, so what you're going to do is this. So what you're going to do is, if I have a binomial now, binom with parameter n and p, okay, how am I going to show that the expected value of x is this, and the variance of x is npq, that you can also rewrite as this? Okay, this is for binomial. Okay, this is for binomial. Now, if I want to derive this from, I'm actually going to come here, because this is what happened. This is talking about one trial, but this is talking about n trial. Now, which means the random variable here is x1 plus x2 until you get to xn, where each of them is binomial. The sum of Bernoulli is binomial. I'm going to say that again. The sum of a Bernoulli random variable is a binomial. So what am I going to do? And I want to find the expectation of x here. Okay, then it's going to be expectation of the sum. It's going to be expectation of the sum. Okay, now if the expectation of the sum is basically going to be, that is guy just summation xi, I start from 1 to n. You remember in this class we've done something like that, right? Okay, now if I have the expectation of that, then the expectation is going to chase that guy away, leave there for me, and it's going to be summation, okay, the expected value of xi, okay, and expected value of xi, what is the expected value of x in Bernoulli? P, right? Okay, now if it is P, so this is going to be summation, okay, P, okay, now this is a constant, the summing P in a, in n time is going to make this guy to be np. So which means this guy is n when it comes to summing constants. Does that make sense? So we're using what I call the sum, the mean of the sum of the random variable principle. Okay, the linearity of expectation is what we're using here. So this is how we derive the mean of the binomial, putting into consideration Bernoulli. Any question? Now let's go to variance. The same thing is going to be applicable to variance. Now the same thing is going to be applicable to the variance. Okay, I have x. I got x equal x1 plus x2 until I get to xn, and I want to find the variance of x. Okay, and of course x1, x2 up to xn are independent. If they are independent, I can only talk about variance. The covariance is going to be 0. Does that make sense? Because they are independent. So there's going to be the variance of x1 plus x2 until you get to xn. Okay, the variance of that, and this is going to be variance of x1 plus variance of x2 until you get to the variance of xn. Okay, take a look at that. Now if you take a look at what we have now, this is more or less like summation variance xi. Okay, now I start from 1 to n. Okay, now what is the variance of x in Bernoulli? The variance of x in Bernoulli is p into 1 minus p. So what I'm going to have now is summation. I start from 1 to n. Okay, p into 1 minus p. So this guy is a constant. Then this guy is basically going to turn to n. Look at that. This is the variance of x. Okay, that is the variance of x. Now I've walked you through the derivation for discrete uniform, for Bernoulli distribution, and for binomial distribution. Now, what I want to do now is moving to another distribution that we call geometric. Okay, geometric distribution. Okay, so x follow geo with parameter p. The probability of x is basically going to be p 1 minus p raised to power 1 minus x. Sorry, x minus 1. And x is going to start from 1, 2 to infinity. Okay, now if I have this as the probability mass function for geometric, okay, now I basically want to show the mean of geometric is 1 over p. Okay, the variance of geometric is a p, is a q over p squared. Okay, we want to derive that now, and I need you to focus the board. Okay, so how do we show? Okay, and you can also work this out. How can you show that this is a valid PMF? When you sum this, it will give you 1. So practice that for all discrete distribution. How you're going to show whether they are valid probability mass function. Okay, the sum of that must actually be equal to 1. Okay, that's how to show that. Okay, now what I want to do now is walking you through that of the geometric. Go ahead. I've gone through all of them, but I've not gone through proofs. I think I only explained. So today's class is just about mathematics, what is behind the scene. I've already told you the meaning. Okay, we've done example on geometry, binomial, and stuff like that. Okay, now we want to look at, want to derive this, want to derive that. Okay, now expected value of x, summation, s is going to start from 1 to infinity. Put into consideration their state space. They have different state space. Okay, Bernoulli 0, 1. Binomial 0, 1, 2, 3 to n. Okay, geometric 1 to infinity. You see that, right? Then for negative binomial, s is going to start from r to infinity. Okay, now, so here, x, probability of x equal to x. Okay, so summation, s start from 1 to infinity. Okay, now x, this guy here is the distribution, p, 1 minus p raised to power this. Okay, now recall that p plus q equal to 1. If p plus q equal to 1, okay, q is going to be 1 minus p. So if I want to rewrite this, I can write p summation s start from 1 to infinity. Okay, x q raised to power that. Why am I bringing p out? Because I'm summing with respect to x. P is going to be a constant, and it's basically going to leave. Okay, it's basically going to leave. Now, when you take a look at what I have now, those of you online, can you still hear me, right?
Yes,
Can
we
you
can.
confirm if you're still hearing me? Those of you online by talking?
Yep.
Yeah.
Okay, thank you so much. Okay, now, when you take a look at this guy, that's a derivative. Like d dq of q of x is going to give you this guy. So if I want to rewrite all of that, what I'm just going to do is expected value of x equal p, okay, summation s start from 1 to infinity. That's what I'm going to have right now. The derivative of that is going to replace that. Okay, now I'm actually going to have p d dq, bring it out, then I'm going to have s start from 1 to infinity, q raised to power x. Go ahead. You say what? Why is not es? Okay, this is what happened. If you have this, if y equal to that, what is the y ds? The y ds is going to be 5x 5 minus 1. So we are different. This guy here is the variable. X is a constant. X here is more or less like this 5. So it means you are differentiating this guy with respect to q. Does that make sense? Okay. Now, if you take a look at this guy now, is I'm actually going to have the q. If you take a look at this guy, is q plus q squared up to infinity. So this is geometric series. Then you now need the formula for sum to infinity. Sum to infinity in geometric series is this guy, a over 1 minus r. What is a here? Your a here is q, and your r is going to be common ratio. The common ratio is going to be q squared divided by q is going to be q. Of course, here, if you want to continue, this is going to be this. It goes like that. Look at that. S start from 1, You see that? Then if I want to rewrite that guy now, so this is what I'm going to do. So if I'm going to write that expected value of x, okay, equal p, okay, is then q, okay, divided by 1 minus q. A equal to Q, R equal to Q. Now, uh, let's take a look at that. Okay, very well. Uh, you have this one here. Now, you're now going to write D, dq. Okay, don't forget this guy here. We use this formula here, right? We have P D dq, right? I now need to differentiate this guy using quotient rule. I want to differentiate this guy using quotient rule. You know quotient rule? Okay, the quotient rule, uh, quotient rule of calculus, okay, is going to, when I have a rational function, this divided by that, okay, uh, for instance, if y equal to v over u, or sorry, or u over v, okay, so the y, okay, the derivative of y with respect to whatever, it's going to be v du, like in this case now I'm talking about the y dq. Okay, v du dq minus u dv dq divided by v squared. So in this case, okay, your q is u, okay, 1 minus q is v. So applying that now, I'm actually going to have, okay, this p here. Okay, now v, what is my v? 1 minus q. Okay, the derivative of u, okay, 1 minus, what is my u? Okay, q. The derivative of v, negative 1, divided by v squared, 1 minus q all squared. Look at that. That's what I have now. Okay, then I need to simplify that now. Okay, now on getting here now, expected value of x equal p into, okay, 1 minus q, okay, plus q, okay, divided by 1 minus q all squared. Okay, this cancels that. So here I'm actually going to have p divided by 1 minus q is p. Okay, so by the time that's reduced, that I have expected value of s to be 1 over p. Okay, that is how that is derived. Now, how do I derive the variance? The variance of x is expected value of s squared minus expected value of s all squared. Now, I need you to take notes. We can't get this direct when it comes to two distributions. Number one, geometric. Number two, negative binomial. We can't get this direct. Okay? Now, this guy, when I have s squared, okay, s squared is the same thing as this. Do you agree with me? S squared can also be written this way. Let's see. This times that, s squared minus s plus s, that will be s squared, right? So when you are looking for this, right? For two distribution, you can't get this directly. Geometric, negative binomial, you need to fall false. Now, if I introduce expectation now, it's going to be expectation of this plus the expectation of that. Look at that. Expected value of s squared equal to all this. If I now want to rewrite the variance, okay, if I want to rewrite the variance, this is what I'm going to do. So if I want to derive the variance, okay, what I'm going to do is the variance of x, instead of expected value of s squared, I'm going to write all this. I'm going to write expectation into x minus 1 plus expected value of x, okay, minus this guy, minus expected value of x all squared, okay? But right now, I don't know this guy. I don't know this guy, but I know the expected value of x. What is the expected value of x? 1 over p minus 1 over p all squared. Now, what do I want to get? I want to get this guy now. The moment I get that guy now, evaluating will be easy for me. Okay, now let me now walk you through. I want to get this guy now. X into x minus 1. Okay, it's going to be summation x into x minus 1, the probability of this, okay, for x start from 1 to infinity. Okay, now if I want to get that guy now, so what I'm basically going to do, oh my God, the 8 is too much. Hope you guys are not suffering from it, right? That 8 is kind of too much for me. Okay, now if you take a look at that now, expected value into x minus 1 equal, okay, summation s start from 1 to infinity, okay, x into x minus 1. What is the distribution? P 1 minus p x minus 1, right? Okay, now we can rewrite that as p s start from 1 to infinity, x into x minus 1, q raised to power that. Okay, now the other time, there's no when I there's nothing like this. When I have x and q raised to power x minus 1, I write it as first derivative, right? But there's something I'm actually going to do now, because we want to make this to be a second derivative. How is it going to be second derivative? And I'm going to show you something now. Take a look at this. If I have q raised to power x, what is the first derivative with respect to q? Okay, so dq is this, right? What will be the second derivative? I want to differentiate this guy now. The square qx, the q squared, right? X, right? Any question about the second derivative? Okay, take a look at this. Compare with this guy. But this is having minus 2, right? But this is having minus 1. I can do mathematical manipulation. If I convert this to be negative 2, then I'm going to put q here. I haven't done anything. Q raised to power 1 minus 2. 1 minus 2 is minus 1. Does that make sense? Any question? Now, because of that, I'm now going to call this. I'm going to say expected value x into x minus 1 equal pq, then the square qx, the q squared. This now can be written as the second derivative. You saw what I did initially? It was x minus 1. I introduced a q raised to power 1, and I introduce another q raised to power minus 1, and they actually cancel out. Okay, now the next thing I'm going to do now is this. Don't forget you have a summation, right? Then the q is going to come out. So I'm going to have pq, okay, pq, then d squared, the q squared summation s start from 1 to infinity q raised to power x. I brought the second derivative out, leaving the one I have q raised to power x, because I'm summing from x start from 1 to infinity. Now, this is pq, the squared the q squared, okay, this guy, you remember what we applied the other time, right? Sum to infinity, which is q over 1 minus q. If you remember, we use sum to infinity formula, a over 1 minus common ratio. The common ratio is a q, and the ratio is q. So here, this one is going to become q divided by 1 minus q. Okay, you now know what I want to do now. I basically want to go. I'm gonna have the second derivative for this guy. I will do the first derivative, then I will differentiate again. Then after which I'm going to simplify. Okay, you can see why the idea of calculus is needed in this course. Okay, now if I want to differentiate this, I'm going to use quotient rule, okay, of u and v. Okay, v 1 minus q, differentiate that 1 minus u, differentiate this guy, okay, divided by 1 minus q all squared. Okay, by the time, and don't forget, when you differentiate that, this one is going to reduce. I'm actually going to have d dq. Does that make sense? Initially it was second derivative. After differentiating, and you have this, it's going to reduce to first derivative. And after simplifying this, then I'm going to, do that again. So right now, so I'm actually going to have d dq, okay, simplify this, 1 minus q plus q divided by 1 minus q all squared, okay. So what are you going to have? So what you're going to have now, so what you're going to have, don't forget, expected value into x minus 1 equal pq d dq. So what do we have from there? We got 1 minus q raised to power minus 2. Let's see, because this cancel that, 1 minus q raised to power 2, by the time you take it up, it's going to be this. You know what I want to do now? I want to differentiate this guy because of the d dq. Okay, so if I differentiate that guy, I'm negative 2, negative 1, 1 minus q raised to power minus 3. Please make sure you revise your calculus notes. Okay, now if you take a look at this now, okay, that is going to be 2pq. Okay, this guy, 1 minus q raised to power 3. Negative 3 can be a denominator. Okay, so I'm actually going to have 2pq. This is going to be p raised to power 3. 1 minus q is p. So what do I have now? So this can reduce that. I'm actually going to have 2q over p squared. Now, if I have that over p squared, okay, I'm now going to go back. I'm going to go back now into the variance formula. You remember the variance formula? The variance of x is expected value of s squared minus expected value of s all squared. And we said this can be written as this, okay, plus expected value of x minus expected value of x all squared, okay. And this guy is what we derived there, okay, 2q p squared plus, what was the expected value of x? 1 over p, right? Minus 1 over p squared. You are back at algebra now. I remember when you were in high school, you're going to say, why are we doing this? We're back to high school now. So what is the SCM? P squared. Okay. So that is going to be 2q plus, okay, p minus 1. Take a look at that. Okay. Now, if I have this now, I can rewrite this as q plus q, 2q, q plus p minus 1 divided by p squared. Oh, that is 1, right? It's going to cancel that guy, right? What do I have? Finally, the variance of x is q over p squared. That is how we derive it. Any question? This is what happened behind the scene in statistics. For you to be able to understand theory of statistics is mathematics. You need the knowledge of calculus. You need the knowledge of algebra. Okay, to be able to, because we don't just have formula in statistics. Okay, mathematical knowledge is what we apply that led to the formula that we're using in the world. Okay, and that's what I've just showed today. I'm going to continue from here tomorrow. Do you have any question? Is there any question? I think I'm going to advise that you visit calculus. Okay, revise your knowledge of calculus. If there is any one of you who have trouble time understanding some basic calculus you need in this course, please visit with me during my office hour. You don't need to, you can be anywhere in the world to attend my office hour. You get what I mean, right? You can be anywhere in the world to attend my office hour. Okay. I meet in person. I also meet on Zoom. Okay. So that I can walk you through the calculus you need, for those of you who have lost touch with calculus. I won't deceive you. You need a lot of that knowledge in this class, because this class is not an applied class. It is called theory of statistics. Okay. Okay. In the absence of question, make sure you all stay safe and have a very wonderful day. Bye for now, everyone.
Thank you.
You welcome.
Thank you.
Thank you much.
You welcome.